for joining our talk after lunch. Hope you have good food and good time at Black Hat. My name is Alex. We also have here Mickey and Jesse. We are from Eclipsium, doing firmware and hardware security. And as a result of our daily work, we are releasing the research quite often in this area. In a couple of recent examples, so like we released the system firmware vulnerabilities in Supermicro, pretty interesting unsigned firmware updates. We're releasing the evil maid attack without opening the case or USB debug capabilities. Also, we released like how to apply Spectre vulnerability to the system firmware, and especially to the SMM runtime part of the system firmware. But today here, we want to present some really new research from us, remotely attacking system firmware. In this research, we will focus on what kind of new capabilities system firmware have, and what kind of new risk this capability adds to the system firmware. Over this talk, we will go over the list of the remote vectors as an industry problem with example from the other research and our own research done in this area. Then we'll go details about the exactly findings which we have in the system firmware in remote vectors. Go over exploit, having the demo of the exploit, and we'll talk a little bit about mitigations and the detection capabilities which we can apply for this type of problem. If you think about technology stack, there is a bunch of good application running in a user mode, like browsers, Office, and other applications. And then you have the kernel mode or ring zero, when you have the operation system and drivers, which is managed hardware resources to provide the capabilities to the application. And we have a lot of good security here. We have like internal teams, which is validating these products. We have the bug bounty program. We have a bunch of exploit prevention capabilities like CFI and all other capabilities, which is recent years with adding to this stack to the user mode and kernel, which is raising the bar for the attacker. For attacker to compromise the system, they need to run the remote code execution, then they escape from the sandbox, then run local privilege escalation, tie a bunch of exploits. So pretty complicated work to compromise the system and pretty expensive. So, but there is another part of the technology, which is hardware. From server to desktop to network gear, ATM machine, AVI system. So there's a bunch of hardware. And historically, we think about hardware as a monolithic trusted block. But last decades, the situation is changing. Hardware become much more complicated. So this is the lower end example of the server motherboard, which has between 10 and 20 different components, call it controllers. And these components communicate with each other over the buses, which was designed many years ago. And that these components may run a software called the firmware to management capabilities of this device, of this controller. This firmware can be from different vendors. The components can be from different vendors. It can be really old, and the code may not be updated long time. This may be compiled with old compilers, which may not have the exploit prevention capabilities. Like in some of the example, it could be stack executable. Some of the example there is no SLR and DEP and so on. In many cases, this firmware may not be updatable, so you cannot update the firmware in these devices. So there's vulnerabilities there that will live forever. And there are, of course, many vulnerabilities in that components because the code is not updating often. In some cases, if it is updatable, the update may not be signed. So you basically can use legitimate interface to update the firmware on the devices, and an attacker can do it without any problems. And last point is that in many of these firmware, there's no read interface. So you cannot make a you cannot monitor this device at a runtime. So that's showing us overall the problem about the firmware and the hardware for the modern system as a blind spot, as an area when the security researchers should get more and more attention. And if you're talking about what kind of hardware firmware vectors of attack we have, we can split it for two categories. One is which is require physical access, like EvilMed attack, which we was releasing a couple of weeks ago, which demonstrate what you can do with 5 minutes of the access to the enterprise laptop. So you can basically infect it with the stealth implant. But there's another part, software attacks. And that software part may have different vectors itself, like it may be software attacks from the operation system, it may be software attacks over different components, and so on and so forth. There was many examples for the last years about all of the software attacks for the system firmware from other components as well. But there is also remote attacks, and usually we think about remote attacks for the firmware is something which is not really often because there is not many network stack implementation, there is not many network interfaces there. But in reality it's not that. In reality many of the firmware components has the network stack. Here's a couple examples. For example, Intel EMEA MT has their own implementation of the network stack, which has an example of the vulnerability released in 2013. BMC itself is the component which is responsible for management capabilities for the servers, which is basically running entire OS with all of the capabilities like OS, including network stack. And there was a couple vulnerability found in HP and Dell servers in the BMC, and one of them will be presented in this black hat. I really recommend you to take a look. But this also showing us that there is a remote vector for the BMC to compromise servers. And nowadays, for the last couple of years, from 2015, we start see that system firmware also incorporating the network stack. Like we have IP, TCP, HTTP implementation in the UEFI based firmware, in the system firmware, in the Tiana core reference implementation. Why we need these capabilities? We need these capabilities because we want to boot our OS from HTTPS, for example. And there is another part of the remote capabilities, remote management capabilities in a modern platform, which is vendor specific. So think about this. So there is a reference implementation part, which implements some functionality, and there is vendor specific part, which is also may implement additional features and may have their own tools for that, their own service. And in this talk, we will focus for this vector, for the system firmware, in a management functionality of the platform, and specifically which is vendor-specific features implemented in some of the vendors. With this, I will switch to Mickey to continue with more details about these vectors.
Thank you, Alex, for that review. I'm going to go into a little bit a further detail into the overview that Alex went in. And we're going to start with BMC. BMC is an acronym, stands for Baseboard Management Control, in case you don't know. It is used in server boards for management, obviously. In the picture in the slide, you can see a zoomed in photo from the previous slide. This is the BMC complex on the motherboard. As you can see, it has its own CPU, SRAM, and flash. It's an independent computing system on the motherboard. It does not require a CPU or RAM or any other peripheral to work from the host. The moment you plug in a power cable, it will boot up, and it is from that point on susceptible for attacks. The BMCs are designed for out-of-band server management. Some of the things you can do with them are KVM, which allows you to VNC over the network to the host, which is the server, and configure BIOS or install an operating system by showing an ISO image to the host, or flash the BIOS, remotely power on or off the platform, or even reset it. They come in different flavors of licensing. Some go in a pay-per-feature model. Some go by tiers. For example, Dell iDRAC have the basic, express, and enterprise tiers. So you pay more, you get more features. In Supermicro, we have pay-per-feature. We have personal experience with that. when we accidentally bricked one of our X10 servers and we couldn't physically flash it. We didn't succeed for some electrical reason. And we had to go purchase a license from Supermicro to go through the BMC and flash a recovery image. That worked. From an attack surface perspective, over the network, when you look at the BMC, you see the IPMI, the IPMI protocol, the VNC port, and the web interface. It is very, very hard to scan BMCs. It takes a long time. But if you look at a little bit more detail, sorry for the horrible slide, there's more than network on a BMC. Right? We have the LAN or the NIC, where the BMC shares a network port with the host or has its own dedicated network port, and the serial connection, the IPMB and the ICMB bridges, as well as other connections going to the host. For example, the system interface between the BMC and the host, think about it as two computers. The BMC is one computer, the host is another computer, and they communicate between each other. Now, if I were an attacker and I would want to hop from the host to the BMC, I would use this connection. Usually what happens is in data centers and enterprises, you'd have the BMC on one network segment and you have the host connected to a different network segment. So you'd have a management network and a non-management network. As an attacker, jumping from a non-management network to a management network is ideal. The short history of IPMI. 1998, the IPMI spec comes out. 2001, it gets its LAN additions. In 2004, it gets a few more additions with VLAN and firewall. And then we start seeing vulnerabilities in 2013, 2014. The famous ones are H.D. Moore and Dan Farmer, where they scanned the internet and found 300,000 BMCs and 53,000 of them were vulnerable to Cipher 0 authentication bypass. And most recently, a vulnerability which I think should win the Pony Awards is the HP ILO4 authentication bypass with 29 or 27 A's. The MEAMT. Unlike the previous zoom-in picture, I cannot show you the CPU. It has a dedicated CPU, it's in there. It says its own SRAM. It also shares RAM with the host. It steals a little bit. And it loads its code from the main platform flash. If BMC is management for servers, then AMT-AME is management for enterprise clients. Think of it as an equivalent platform in functionality, but not the same physically. Enterprises use these to provision systems, to allow IT professionals to install OSs remotely, configure BIOS and hardware and firmware. Attack surface from a web perspective. If you look at the open ports, AMT has a web interface. We all know the famous vulnerability from a year and a half ago that allow you authentication bypass. And the standard ones, VNC and serial over LAN, and there's so many features, we're not going to go into it. A little brief history of that. We first encountered AMT in 2006, 2007 added wireless support, 2008 provisioning over the network, 2010 remote KVM, and 2017 is when we see the first major vulnerability. A brief recap of that vulnerability in case you never heard of it. It was an authentication bypass where you could send an empty digest to the AMT and it let you authenticate and log in. And there's a few more in 2018, we haven't added them, but Intel released a month ago advisories explaining they found a few more vulnerabilities that they patched internally, which is nice. Kudos to Intel for disclosing publicly things they found internally. BIOS, okay. If you don't know what BIOS is, I'll go briefly over that. It is essentially the early code that configures the hardware before loading and transitioning execution to the operating system. What I mean is by configuring hardware is it is setting registers, configuring memory, memory protections, setting SMM, locking down the configurations with bits that you write once to them, and after you write once, they're set, and you have to power cycle the platform to change them. It also sets protections on its own flash, so no one other than itself can write and read from it. Write to it. Read from it, it can't. The code is main CPU, flash, RAM, mainframe. It's part of the main platform. BIOS is the keyword of trust that everything that works afterwards relies on. So if you compromise BIOS, you win. BIOS, in the early days, everyone had their own version. In 1998, Intel said, let's get our heads together and do something about it. They wrote UEFI 1.0. In 2002, it evolved into a forum, and more companies started to adapt it. 2007, they added more cryptography, network authentication, more of that. 2015 is interesting. More functionality starts to pop up. Wi-Fi, Bluetooth support, HTTP, HTTPS adds in 2016 with the introduction of OpenSSL. And in 2016, we have a publicly disclosed vulnerability in the core code, which also is called Tiano core, where Topher Timson has discovered there is a missing size check in a DHCP packet. The interesting fact about that is there was a check, it was in an assert. They fixed that. Now let's look at the reference implementation for the UEFI 2.4 spec as an example. You can see that there is a lot of functionality here for if you want to do PXE boots over v4, IPv4, IPv6, iSCSI as well. You see there's TCP, UDP, IP4, IP6, and DHCP, and so on and so forth. On top of that, that's what the reference code gives you as a vendor, as an independent BIOS vendor or IBV. HP in 2015 saw that reference code and decided, okay, we need to add more. So they, based on that implementation, they added their own implementation for HTTP boot. So what you see in blue is HP's addition. In tinted green is what the reference code offers, and the pink bottom is the hardware layer. This is a perfect example of what vendors would do when the reference code does not fit their needs for the market they're targeting. Another example for that is AMI's addition for the Bluetooth stack in BIOS. The reference core code does not have support for, it has some support for Bluetooth nowadays, but in 2017, AMI decided to implement their own Bluetooth stack. Basically, it's Bluetooth in BIOS. I don't know of any use case for this, but it allows you to connect to it before the OS boots. We did actually find a Dixie module in a production laptop that is Bluetooth SMM. So it is used in the wild. Another great example for adding to an existing functionality is AMI again, where UEFI, the reference code, offers a Wi-Fi stack, but it's not complete. So they would have open network connections and WPA2 connections, but they didn't apply EAP. So AMI came along and implemented their parallel driver for the Wi-Fi stack. So you get these two ecosystems, one next to each other, and that's something that is worth noting. And with that, I'll pass it on to Jesse.
Hi, thanks, Mickey. So I'll take over a little bit, and this is an example of a feature that has been added. Like HP had their own version of HTTP boot, and it eventually was a similar functionality pulled into the official UEFI specification. So the UEFI specification and reference implementation now has HTTP boot also. This was basically done to replace PXE, which was the older version of remote network boot. This actually allows you to configure a URL and download a UEFI application that's run as a bootloader, or even like a complete ISO image over HTTP or HTTPS. It will mount, it basically has a RAM disk functionality where it will download the ISO, mount the RAM disk, and look for the UEFI bootloader in this ISO that it downloaded, which is kind of cool. It does do signature verification before executing this UEFI. There's basically policy bits that specify if a UEFI application comes from this location, check signature. If it's coming from an internal firmware volume, don't bother checking signature. But because it's from a remote source, it does check that signature verification in order to maintain the secure boot chain at this point. So intelligent provisioning is kind of an interesting feature that we ran into. This is a feature in HP servers, and it essentially is kind of an embedded system in HP where BIOS can transition into this alternate environment that it can download firmware updates, can apply the firmware updates. It can actually download drivers for your hardware from the internet and inject those into your previously installed operating system. So it'll mount file systems that have already been installed and inject new drivers into the system, which is kind of cool, but makes me a little nervous also. It also has some functionality where it's kind of like this wizard version of simple configuration and provisioning of the operating system. So you can configure a bunch of different devices, use this provisioning capability, and it'll install Windows or SUSE Linux or different operating systems from a configuration file instead of manually going through the operating system installation steps. So one other thing that we ran into is SMTP from UEFI. So this is a feature that from BIOS, it will bring up the network connection, get a DHCP address, and connect to remote email servers to send email for you. In this particular example, it was designed to be used for a diagnostic tool where you can report an issue back to the BIOS vendor's technical support team. A really interesting feature of this particular feature is that they have an NTFS driver in this BIOS that this feature can use that NTFS driver to mount your hard drive partition. You can browse to any file in the file system and attach it as an email as long as it's less than 3 megs and send that from BIOS before the operating system ever loads, which is kind of neat. This feature and functionality is there present in the BIOS. So if someone is able to compromise BIOS, all this framework is there that you could take advantage of and potentially use it maliciously. Another feature that we ran into that's pretty interesting is HP has a remote diagnostic download function where in BIOS you can configure this functionality that will, when you reboot, it will bring up the network connection before it even loads the operating system, go out to a remote server, download an executable from that remote server. In this case, it does check the signature before executing it, like the other, like the HTTP boot. It basically does a similar signature verification check and then executes this executable that you downloaded off the internet. You can either specify downloading it officially from HP's website, or you can have your own custom URL where you put this diagnostic tool or random signed EFI binary somewhere else on the internet, and it'll download it from there and run it. There is the ability to take the results that are output from this tool and upload it back to a different website on the internet. You can specify username and password if it's behind something that's like a FTP server that's password protected, but that functionality is all there in the system. And it's interesting because this one you can schedule it automatically. So every time it doesn't run at runtime after the operating system is run up, but every time you reboot it, it will check and see if it has if enough time since the last check has happened. So if you have it scheduled every week and you reboot your system after a week and a half, it'll run again, connect to the internet, download this, and upload the results somewhere else. So it's kind of an interesting feature. And so another thing that we ran into is historically, BIOS has been kind of difficult to update. So a lot of people don't update BIOS. Like I know I have been kind of lax and gotten better at updating BIOS since I started working on this kind of research. But because it's been such a difficult thing to do, multiple vendors have started adding functionality so that they can basically check if there's a new BIOS update available before even loading the operating system. So from BIOS, it will bring up the network connection, make requests out to remote servers on the internet, potentially download those updates and apply them. And there isn't a standard way to do this in UEFI. So the different vendors have just all made their own implementation, and everybody's done it differently. So there might be some problems with that. Here's an example of, this is what ASRock's implementation looks like. It's basically goes out, connects to the internet, and shows you if there's an update, allows you to update that if a new update is available. ASUS has a similar functionality. It's basically exactly the same functionality. It just looks different, and it's all built on top of those core UEFI network primitives like TCP4 Dixie, the DHCP primitives, but because all the extra update functionality is custom, it's just implemented differently. HB has a similar feature where you can basically do the same thing. You can configure your update source directly from BIOS. You can have it point at hp.com, or you can have it go to your own custom URL here also. And this one is interesting because it'll also, you can schedule it'll automatically download and apply those updates if a new update is available. And this is kind of a difference between, like, this is more of like an enterprise featured or focused feature where it's like, it'll go do it for you. The other ones were like more consumer focused where it's like, the feature is there, but you kind of have to go do it yourself. So as part of our research, we basically discovered that both ASUS and ASRock were doing this insecurely, and they had basic buffer overflows in their update process. So to show this off, we basically wrote a demo to exploit this and see what we can do, and we can show what that looks like right now. So as the tradition is to pop a shell when you are exploiting stuff, or pop calc, we figured we might as well do that. So this is like the BIOS, what it looks like. We're going to go and launch the Internet Flash function and see what it looks like. So this got triggered just by checking if an update was available. We didn't have to go say, okay, go apply the update and actually basically apply the update. It's just checking is enough to trigger this. So we can also have like a bigger payload that's a little bit more elaborate. Like that was a pretty small payload. It's not that interesting, but you basically have complete, you can run much bigger code in your exploit. So this one is actually popping a shell instead. So like the shell application isn't included in this UEFI binary, but we can just include it in our payload, and it takes a little bit longer, but you get a complete interactive shell. You can basically run any arbitrary UEFI application that you want at this point. You don't have to have any kind of visual, like you don't have to show anything on the screen. We did this just so that you could actually see that something's happening, but you could have it be completely silent and then inject something and then continue booting up if you want to. So So once we reported this, ASRock was like, well, uh-oh. They basically provided firmware updates for all effective systems that just disable the functionality. And it was almost 300 different motherboard models that were affected by this. Basically, the last two generations of Intel processors, basically from Haswell onward, and then AMD processors were also affected, but there's, I think, 3 different generations of AMD using the AM4 socket. ASRock's response was, they basically said, this is only happening before the operating system boots, so it doesn't really matter. This isn't a problem. And we went back and forth with them a little bit and tried to explain, no, you actually really should fix this, but they didn't seem to understand why. So this actually hasn't been fixed. So let's take a look at what the exploit actually looks like. And it's a little bit different. So, well, some things will look very similar. So the way this works is, here's the example of ASRock, where it basically does a plain HTTP request out to the internet at asrock.com to this liveupdate.asp page. It does include the specific model of the motherboard that's running. So if you need to return a different exploit for a particular motherboard, you can totally do that also. But it is plain HTTP, and it's possible to man in the middle of that. So let's take a look at what the response looks like. It's basically just an XML document that has some URLs, region information, and then a list of what BIOS updates are actually available. And as you can see, like, we made our description like this is a malicious BIOS. And if you actually run this, the description shows up in the UI and gives you the ability to go and update that BIOS. But we figured out that if you basically just make some of these fields much longer, like if we put a bunch of A's in the URL field, when you're checking for the update, it just hangs, and you're wondering what happened. It's like, I'm not sure what happened here, but we can take a look at this and figure out what's happening. And I'll talk a little bit more about how specifically to figure that out in a second. But first, let's take a look at the ASUS one. It's a very, very similar situation where it's also making plain HTTP requests to ASUS's website. And the structure of the request is slightly different, where instead of an ASP page with a model, they have a specific path that they're requesting for this specific motherboard. And here's the response from the server saying, here's your update that's available for this motherboard. In this case, it's not XML. It's like XML, but a little bit different. And it has a similar issue, where it's like if you put long strings in these fields, you get the same behavior, where the update just hangs. In order to figure out what actually happens at that point and what actually happened, like in an operating system or application, like user mode applications, even kernel mode apps, you have GDB, kernel debugging tools. When you're debugging BIOS, you don't have those capabilities yet, so you need to use some hardware debug interfaces instead. If you look at these three, XDP is the really old, expensive one. Old systems basically had a socket on the motherboard that was marked, sometimes it's even on the silk screen of production system saying CPU XDP or PCH XDP, that you literally had to open the case, plug this into, and then you had this debug capability and you can see what's going on. They've moved to what's called a closed chassis adapter, which basically allows you to do debug through a USB port and figure out what's going on without opening the case. And there's also, so there's the closed chassis adapter, and then there's also just a native USB 3 debug capability, which uses this cable on the right here, which it's essentially just a USB 3 A to A cable where the VBus line has been removed. They all, like the two on the right are essentially equivalent, and you can use those on systems from Skylake and newer. All three of these were made for debugging the hardware, and they're sold to OEMs and BIOS manufacturers so that they can figure out what's going on when they're implementing BIOS and bringing up platforms before they sell them to customers. The two on the left, in order to get those, you can buy those if you're an external customer, but you need to sign up, basically get an account with Intel, sign an NDA. The one on the right, if you have a new enough platform, you can just buy that from third-party vendors and go use that with newer platforms. So it's also a lot cheaper. But basically, those you can then use with what's called Intel System Debugger. It's part of the Intel System Studio package. It essentially gives you capabilities that are similar to GDB, where you can examine memory, you can look at register state, you can look at CPU structures like the GDT table, you can set breakpoints. It's a little bit cumbersome to use sometimes, and also you run into interesting things like, since this is basically like JTAG, so you might need to halt the system, enable your breakpoints, your hardware breakpoints, and then go do your test. So there's a little bit more work, and it's not quite as simple as just running GDB on a user mode app that's crashing. So there's also what's called the Intel debug abstraction layer, which is essentially, it's part of this Intel System Debugger and Intel System Studio. There's essentially a framework that you can write Python scripts in order to go do things and script your analysis and debugging of the system. So once you get into what's going on, UEFI is a little bit of a different environment, just because obviously your normal show call won't work because there is no operating system yet. Like syscalls don't work. None of that framework has been loaded yet. But there are some things that help us out a lot. So first, you're running as ring 0. There's none of these protections are present. So there's no address randomization. Things are at relatively predictable locations. There's an executable stack. It's basically easy at that point once you know what your environment looks like. There's some other things, is that you don't have operating system like Windows or Linux or whatever functions yet, but there is something called UEFI boot services, that those are present, and you can call UEFI boot services functions up until the point where exit boot services is called and the operating system bootloader is launched. So all of that is still present, but you need to know how UEFI works internally to actually take advantage of that and how to use these functions. So a pretty key point of how UEFI works is it's all built on top of this concept of UEFI protocols and protocol interfaces. And these are essentially intercomponent mechanisms for communication. It's essentially like an object-oriented programming class where you can have one piece of code publish an interface that's identified by this GUID, which is a globally unique identifier, of course. And you can basically specify, here's an interface that provides these capabilities, and I want to publish that by GUID, and then some completely other different piece of code says, I want to go use that piece of capability, so tell me where that protocol is, and then you can look up the protocol by GUID and call functions in it. It's essentially, you look up this object and then call functions in the object, and it has built-in function pointers and then some private data, exactly like a class. So some of the really critical boot services functions that are useful are locate protocol. That's the mechanism by which you can go find some other part of UEFI. So like all of the functionality that we talked about before with the network stack, that functionality to send email, the functionality to use the NTFS driver to look at your file system, all of that is published. All of those interfaces are published by GUID. So your shellcode can actually just do a locate protocol call from boot services in order to go find the GUID for NTFS, and then call functions in that and do some interesting things. Some other really key useful things for our purposes are load image. This is essentially the key function that's used to load a UEFI executable in the first place. And you can either specify a device path to a particular firmware volume or source that you want to load this EFI executable from, or you can give it a buffer in memory and a size, which is really nice for what we want to do. And start image basically takes the handle that's returned from load image and runs it as an executable and launches the executable. So putting this all together, our payload layout ends up looking a little bit like this, where we have a limited amount of size on that field that we talked about that's overflowed. It turns out that if you have too many bytes there, you cause a pointer to reference that crashes before you even get to the return address. So you only have a limited amount of space in that overflow on the stack itself. But we found that the entire XML document that was downloaded from the remote site is also in memory. It's basically sitting on the heap, and we just, in our exploit that actually goes on the stack in the overflow, we just have a little egg hunter shellcode to go search the heap to go find the rest of the exploit and basically jump there. One thing that we ran into, though, is that the XML document with the rest of our exploit is sitting in the heap. So when it was right before we hit the return instruction and return to our overflowed return address, they called a free function. So our data is on the heap, but it's in no longer allocated space. So if we trigger any allocations, it's going to corrupt our buffer that we want to preserve and we want to execute our malicious code out of. So it turns out that we basically need to copy ourselves out of the heap into a different location, and then from there we can call the load image and start image functions and basically provide whatever arbitrary UEFI applications we want after that. We could go use some functionality that's built into the system. We could bring up network connections. We could use the NTFS driver, but we could basically do whatever we want at this point. I mentioned the NTFS driver a couple times, and the interesting thing about that one is that if you've looked at the hacking team rootkit, they actually, as part of their exploit, they packaged up the NTFS driver with their exploit so that they could use that functionality to, rather than read a file out of the operating system, they would persistently inject their agent into the operating system using the NTFS driver. And that was an interesting UEFI rootkit that you could do essentially that from this exploit. Except you don't even need to bring the NTFS driver with you because it's already on the system. So what can we do about this? There's been some talk in the UEFI forum about hardening UEFI, like doing hardened page configuration, actually randomizing the stack, making it a non-executable stack, but none of that has actually been implemented yet. So we're hoping that this will go in, but it's not even in the reference code. And even once it goes into the reference code, it'll take a while before it shows up in real vendor BIOSes that are being shipped into production devices. So if you are concerned about detecting this, we can detect it with a fairly simple Yara rule if you have an IDS that can feed your network data through Yara, where it's like we just need to look for an extra long URL field, and it's a pretty simple rule. So we can detect the ASRock buffer overflow live on the network with this. ASUS one is basically very similar, it's just a different field. So if somebody has already modified your BIOS, a useful way to detect modifications to the system after the fact is you can use the chipsec tool, which is a really useful framework for exploring hardware interfaces in the system. You can use it to check for known misconfigurations. So like there's a lot of bits and locks and hardware configuration that needs to be set properly in order for a system to be secure once it boots up. And we found many, many issues where BIOSes were not setting everything that they needed to set, or they were setting one part and not setting it in other places. So I totally recommend trying out chipsec. It's also a good frame. It's basically, there's a kernel driver to go get the direct hardware access, and then it's all written in Python. So it's really easy to build new tests and frameworks. So you can use it to explore the system. You can also use it to build exploits and proofs of concept to try things out. But there's basically some built-in functionality that's been added to chipsec to be able to extract the spy image from the running system and then check it against a whitelist that you've built previously. So if you think you've been hacked, or somebody has implanted a system or implanted your BIOS, made some modification maliciously, maybe somebody managed to find a runtime vulnerability, or there's a vulnerability in how it sets up the system so the spy write protection is not correctly configured, and somebody is able to modify that, and you can basically extract the spy and then check it against a whitelist. You can also generate a whitelist. So like when you buy a new system, if you believe it hasn't been tampered with yet, hopefully you didn't have a supply chain compromise along the way. But if you think it's in a known good state, you can generate a whitelist using this second command line here, which will basically parse all of the firmware volumes, generate hashes for all of the images in the UEFI binary, and then later, maybe once you've traveled to Vegas with a bunch of other hackers, maybe you think something happened, you can then go back and check your you can check your system against this whitelist that you generated previously. So it's a really useful bit of functionality. So some basic concepts is that systems firmware is really big, it's complex, it's highly privileged software, it runs before the operating system loads. Also, BIOS has had a bunch of issues where it's been kind of a mess, and it's getting better. Like the update process, it still is a mess. It's hard to update. A lot of people don't update BIOS, but this remote attack surface, it keeps showing up in new places, and new places that didn't have a network remote attack surface now suddenly do. And part of that is just because of trying to fix the problem of doing system updates in the first place. People are adding new exploit vectors and adding new vulnerabilities to the system that didn't exist in the first place. So I think we've reached our end of time. So does anybody have any questions? Do we have time for questions? Okay.